Today is October the 28th, 2017, and I'm going to, hopefully, this is probably about the 10th time I've attempted to make this video to show what the challenges are in measuring a large iron core inductor like an audio output transformer. You have to start with some idea of what you're looking for, and at the same time you have to be careful that you don't just simply find what you're looking for, because that can be biased science sometimes. And I'm going to show you why I can say that. I can prove that to you right here in just a second. It's funny. Okay, a little transformer like this. This is a James output transformer. It's a 20 watt. It's a model 6228HS. Got a 4816 on output. It's got a it's called an ultra linear. You know, this guy right here. Plate, screen grid 1, center tap, screen grid 2, and plate 2. By the way, before I forget it, you know how they say the screen grid is at 40%? Well, I did voltage measurements on it. Absolutely, the 40% using the center tap is 0. This is 40% right here. It actually measures at 43%, which is what some of the discussions talk about. And this measures at 60%. Yes, I know that 60% and 43% is 103%, but that's the way it works. Transformers are strange devices. But I always thought, until I actually measured it until now, I always thought the screen tap, I always thought the 40% would be from the plate down to here. But the 40% is from the screen grid to the center tap. So we have the other 40% over here, which actually, like I say, will measure out at 43%. And then we have the 60% here. This is a fact. You can put in enough voltage right here that you get out 1 volt from here to here. And you'll measure 4.3 volts here, and you'll measure 6 volts here. Okay, let's don't get too wound up in that. There are some real challenges in measuring a transformer. These iron cores, well, I don't know. I don't even know how to grasp this sometimes. You see, I have these little calibration inductors around here, and I can take this little meter right here. This is a fairly inexpensive little meter, and it'll measure them dead on. So will the general radio. So will this little guy right here. This little guy right here, for its money, is actually not too bad. This is actually a fairly nice little meter. But when you start measuring something like this, when you're trying to measure an iron core transformer, you won't get the same numbers every time. And basically, the more you fool with it, the more it changes. It just starts drifting. Sometimes, and I don't want to start it now, maybe I will, accidentally, it'll just start drifting. And the numbers you get just are not consistent. And if you cannot get consistent numbers, if you can't measure the same thing every time, you got a problem. Well, you can come up with some numbers that are realistic. But I got to show you something else about a transformer that might surprise you. Well, let's see. I'll use this same one again. Basically, what we do to get the inductance, and basically what we do to model this transformer is this. We measure the inductance from here to here, and then we measure it from here to here. That's really all of the actual inductance, direct inductance measurements we have to make. Because if we know the impedance of this from the manufacturer, and we know the impedance here, then we will determine what this one is. Okay, now when you measure the inductance from here to here, and then you measure it from here to here, the inductance from here to here is not the sum of these. You measure this one, and then you take the square root of it. And then you measure this one, and you take the square root of it. And then you add them together, and then square that number, and then you get this number. And this number right here, then you do it again to get it across the whole thing. And the numbers you'll come up with is something like, for example, say 2.5 Henrys here, 1.3 Henrys here. 2.5 and 1.3. And then you add them up and you'll come up with something. You can check my math, and this math is not correct, but I'm just giving you some examples of how it turns out. And then you'll say you get 9 across here. And then you do that again. Then you take the square root of this side and the square root of this side. You just double it, add them together and square that again, and then you'll, across the whole thing, you'll end up with like 30 henries, which makes sense. And then you'll say, okay, you know, my measurements and my calculations agree enough that it makes sense. Because the little devices that we have like this, and here, and whatever we might have, just aren't made to work with this. Now, obviously there are devices out there, but I don't have one. I probably can't afford one. Okay, now here's the next thing. Now, in my case, right here, the one that we're working on now is actually a really nice classic case. This side right here is 8,000 ohms, and this side right here is 8 ohms. So that's 1,000 to 1 impedance ratio. Well, it's also 1,000 to 1 inductance ratio. So if we end up with 30 henries over here, we're going to end up, if the transformer coupling is perfect, and it is virtually perfect. It's like 0.9999. If we end up with 30 henries over here, we're going to end up with 30 millihenries over here. And that's the way you model your transformers. And it works. I'm going to hopefully show you that I can measure this inductor right here. I've got it right now. I've got the taps. I'm not going to move it right now. I've got the taps right now on the screen grid in the center tap. And let's get the camera up here just a little bit. I got the wires in the way, but I think you could see through them. I'm going to zoom in on the meter. I don't want to move things around too much because it can start making things, you know, see there? See there what just happened? No, the wires didn't come loose. I probably put some static in it. I just messed it all up. And this is what happens. This is exactly what happens. And you say, well, what's the problem? I had it nice and steady and everything a while ago, and then I moved the damn thing, and now it doesn't work anymore. Now I'm going to get completely different answers. Well, before I moved it, this thing was peaking out, or dipping, excuse me, at about 1.37 henries. 1.37. Remember, I was giving you some ballpark numbers just a second ago. So, after this thing sits there for a long enough period of time, you can kind of come up with something, and it makes sense. 1.37 henries right here. From here to here. Now again, like I say, we have to be careful about what we're looking for because we tend to find what we're looking for. Let me show you another good example. Now that I've messed this up, I can't. This is the problem. Now, there are some very well-intended suggestions out on the internet to put like a capacitor. Like this is a 0.047. Call it a 0.05. If you put it in series with a winding, say the plate winding in the screen grid, and then you put an oscillator across it and you vary the oscillator, you can find its resonant frequency, and indeed you can. And then you use the formula of the resonant frequency equals 1 over 2 pi times the square root of LC, and then you will calculate the impedance. And it won't come out to be anything like you expect it to. Or you can put it parallel and you can put your meter across it. When it's parallel, then the impedance gets very high at resonance, and you'll have a peak voltage across it. When it's in series, you'll have a low point at resonance, and you can measure the current through it. The current will be at a maximum. But these don't work. They will not give you the answers that you expect. You'll get all kinds of crazy answers, and the harder you work at it, the worse it gets. This is not to discourage anyone. It's actually to encourage you. You have to be very careful. Now again, you can take these little guys right here and measure them, and every one of these meters will give you dead on. Here's a 500 millihenry. Here's a 66 There's 68 millihenry. Can't hardly see it without my glasses. Here's a 10 millihenry. Let's see. There's some dandy 17 and a half henries. See? And it'll measure those right. And here's the beautiful 1 Henry. Spot on. Different situation. Okay, here's another way you can trick yourself. This is again what I'm talking about finding what we're looking for. Let's look at this guy right here. Everybody's seen these blue ESR meters, right? There you go. Let's measure the impedance across. Let's measure the secondary impedance, because this thing is an AC ohm meter. So it's actually giving you an impedance. A scalar impedance, not a complex impedance. It only has the magnitude, the R value. It doesn't have the imaginary value. But let's say we want to measure this thing and we put it across common and 8 ohms. Well, look at that. Isn't that marvelous? 8.7 ohms across 8 ohm tap. What about the 4 ohm? 3.6. Holy mackerel. 15 ohms across a 16 ohm tap. This thing is a miracle. Well, it's not. It is a miracle. And it's cool. But it's not. Okay? Wow, that is great. Why don't we just use that? Okay? Well, let's use this one. Here's a big transformer. Look at there. 8 ohms. You can see that just from 10 to 11. 8 ohms. 8 ohms from 10 to 11. Let me find 10 to 11. Right here. 10 to 11. Let's see what it says. It should say 8 ohms. Man, this thing is spot on. This just solved all of my problems. Well, darn it. Sorry for the fumbling. Always needs something else. Well, I'll just hold it there. 16? Well, that didn't work, did it? Okay, anyhow, I have very painstakingly and over a long period of time letting this device right here settle down. I've come up with numbers that really make sense, and that's the numbers we're going to use to model these transformers. But unless you've got some very nice and specific device, or you can come up with some circuit that I certainly cannot come up with. I have tried a lot of things, gentlemen. Maybe I haven't tried everything. And maybe you guys can suggest some way that actually works, and not just something that's read off the internet where, like I say, intentions are good, but they don't work for devices like this. Now, resonant LC circuits like this with little coils, like for RF, especially in the 3 to 30 megahertz range for amateur radio, that's called the HF, the high frequency range, I think it works great. It works every time. The numbers are consistent, the values are correct, and it's the only way to go. It works, but it does not work for these big iron core guys like this. And I say big, 30 henries, you know, an output transformer could be as high as 100 henries. But the way that you calculate it is kind of interesting, isn't it? It's not a direct measurement. I don't think anybody, I don't know, I guess, you know, some laboratories have something that they can measure across and measure all these and just come up with the numbers. But that's actually how it's done, the way I just described it, so I won't do it again. Okay, so with that, we're going to take the numbers that I have painstakingly derived, measured and derived, and plug them into our models of LTSpice. LTSpice is just a fascinating program. You can model your transformer. You can make the perfect transformer in a push-pull circuit, and you get no second-order harmonics. That's kind of cool, because that might allow us, if we model it correct, to see what second-order harmonics might be created further back in the circuit. So you can model the transformer and then just drive it from a voltage source, for example. You can get FFT displays out of the LTSpice. It takes a little manipulating it, otherwise you'll get kind of a goofy one. But just a fascinating program. I'm having a lot of fun with it. And once you get used to it, there's a rather sharp learning curve, steep learning curve, I think is where it's mostly expressed. It'll take you a week or two playing with it several hours a day, and it can be pretty frustrating. But there are a lot of models already out there you can use, and then you'll pretty quickly learn how to draw your own. And then when you print it, you print a beautiful schematic. If you've actually modeled it and you know how to, once you learn how to simulate it, you can just does a marvelous job. Really a lot of fun. It's all free. It doesn't cost you a penny. I can't think of anything else I'd like to say right now, but we'll get to the software program itself, and you'll see how this works, how you can cut and paste from one to the other. I think I'm even more fascinated by playing with the LTSpice program, but I had to show you that just hooking up a little meter to this, unless you've got something from an audio laboratory, it just isn't that simple. Let's move on. Actually, before we go to the computer, I got to show you guys how I get the second number here, how I've gotten these numbers. Okay, this is across, whoops, let's zoom out here. This measurement right here is across plate to screen grid 1, and we get 2.55 Henrys. So there's our 1.37, there's our 2.55. You do the math, like I showed you, get 7.66. You do the math again, and you get 30.64 Henrys across the whole thing. And since this is an 8,000 to 8, an impedance ratio and an L ratio of 1,000 to 1, we get 30.64 millihenries over here. We don't have to measure this. If we did, I'm confident we can come up with it. I have done it. I don't think it's necessary in this case because I've done it enough times. So we're going to move on from there. And furthermore, you might ask, why do I use this? Well, this is obviously a laboratory grade instrument. The little meters like this are just jim dandy for a lot of things, but again, for the iron cores, I don't think they work. And secondly, this guy right here gives us the Q. You have to turn this right here, the D and the Q. The D stands for dissipation factor, and the Q stands for quality factor. Well, the Q, the quality factor of this one, is on high Q scale at 7.5, and we know that the Q is equal to X over R. Q equals X over R, and we measured the Q as 7.5. That came right out of our instrument here, and we measure R if we need to, and we will. I have, and we can derive X, and we can use that if we want to, maybe for shunt capacitance. It's complicated. There are so many numbers. I'm not trying to be vague here. I'm just trying to keep from making this so long and complicated and stumbling myself up somewhere along the line too. It's easy to do. Okay, so we have another set of numbers from this, and in a debate of which one's right, I would use this GR to evaluate this rather than the other way around. Of course, on the small devices, they agree, and having them agree is really kind of nice, of course. So there you go. Had to add that in. Okay, let's continue modeling the transformers. We'll start LTSpice right down here. And the transformer that we just got through measuring is this one right here. It's called the Macintosh MA230 channel. That's the voltage amplifier in it with the James transformer. I've labeled it best model. And there it is. If you want to look at just parts of it, you can roll your mouse and look at. There's the transformer right there. The nice thing about the GR instrument is it gives us the Q, and Q is the reactance over the resistance. So I've measured the resistance across half, and then I measured the resistance across this half, and I assumed it was capacitive reactance, so I came up with 174 picofarad shunt here and 174 picofarad shunt here. Now you can take this thing to the level of insanity, and you can put some off the ground, and then you can put another one off the ground, and then you can try to shunt some between them, and you just got to figure out at some point just how insane you want to make yourself But these transformers actually model really fine and don't take up your whole life. And right here is the case statement, the coupling statement between L1, 2, 3, 4 and the secondary. I just made it all 0.9s. That's kind of an easy way out too. You'll find out a lot of people do that, and in the beginning I thought, well, they were just being lazy. But what you end up finding out is there are so many variables that everything's a compromise, and just being able to measure it. If you can measure this one and you can measure this one and you know the impedance, then you calculate the rest. This actually comes out to be like 30 microhenries, actually 30.64. So this one comes out to be 30.64 millihenries. Okay, so with all that said, see, let's roll our mouse. All you got to do is press the space bar and it fills one space. I hope this turns out good. Let's run it. And I think it's already run. Now, you know, when you put your little thing down here, you get that little red pencil, you get a voltage reading. When you put it across a component and it looks like a little clamp on ammeter, you get a current reading. So I don't think it matters. Let's just get a voltage reading. We're doing a sweep statement right here. You can go over here and change it to whatever you want. I think I've shown that. I'm not sure. I made so many of these videos. You can change it to a Cartesian. I don't really want to go over all of the details of this. You can play with this stuff for hours and hours and just drive yourself completely nuts over it. But with that said, I'm going to try to keep this kind of short. Let's see. Let's close it. Let's run the simulation again because it runs so quick. Now let's look at the current. Whoops. I'm putting it over the wrong thing. Let's look at the current, and there's the current. Now, if I did a simpler statement, which I wish I had, let's see if I can do that. I probably can't. Not gracefully here and without taking up a lot of time. Let me see if I can load one more file. Well, here's one that we really do want to look at. Let's see. Let's look at this one called Modified Transformer. Let's see if this one runs with just a transient statement. So you don't have to watch me. Yeah, this is a good one. Okay. See, we got 30 volts peak right there. See, right there's 0. So we got 30 volts peak, 30 volts negative peak, 30 volts peak, or 60 volts peak to peak. And then if we put that was our voltage reading that we got from this little red probe. Now if we put our current meter, our current clamp across the output resistor, across our 8 ohm load right there, and click on that, now the right scale over here tells us we've got 4.2 amps. Now, without getting too weird into the calculator, I guess I got to turn on a little bit of a light here. I don't want to glare us out. If you do the math there, what you have to do is the RMS voltage is from 0 to 30. It's 0.707. 0.707 times 30. And the current is going to be 0.707 times 4.2. You can read these numbers by putting your cursor on it. Let's put our cursor right there. If I can leave it there. As close as we can. Sorry. And then look down here in the corners and you can see it. Y equals, the voltage actually equals 30.00. And the current is 4.2. So if you multiply each one of these times 0.707, then multiply them together, then you get the power. You get the average power. It's not called RMS power, by the way. I really don't want to get into that. But there are some videos about it. It's called average power. It might be what you're thinking of as RMS power, but RMS power really doesn't exist. There's already videos made on that, so I don't want to draw this one out with that discussion. Okay, now let's move on to an ideal transformer, and then we'll bring this to a close because I want it to go well. I want you to see this. It's just really some really interesting stuff here. Okay, look at this transformer right here. look at this one. It's very simple. It has no resistance in it, has no capacitance in it, it has no leakage inductance. It's just 3 coils perfectly attached together with a 0.99995 coupling factor. It's got a 10 Henry and a 10 Henry. Well, if you do the math there, if you do 10, if you do 10, and you take the square root of it, store it, and then you do 10 again, take the square root of it, add it together, and then square that, you get 40. I don't know if you can see that or not. You get, that'll be 40 Henrys. Now with 40 Henrys, and then we take this one right over here, the 0.064, that'd be 64 millihenries, and we divide that, 0.064 divide. I hope you can see these numbers just a little bit. It's kind of important. That is an impedance ratio of 625. Okay? And if we take the square root of that, that's a turns ratio of 25. If you've played with transformers and amplifiers much, you probably going to start recognizing this. A turns ratio of 25, so it's an impedance ratio of 625. So if we put 8 ohms over here, we know the reflected impedance over here is going to be 625 times 8. Look at that. What is that? 5,000 ohms. What's 5,000 ohms? That's the perfect match for a pair of 6L6s. That's ideal. Look here, we got the 6L6 over here. We got 240 volts on its screen. We got 415 volts on its plate. So this is like the ideal transformer. Now, here's something that really is neat about this. So you press the space bar, it gets back in the middle. Let's run it. It takes a few seconds for this to run. I think you can see the down here, that's 6%. But let's let it run and I'll show you something that'll surprise you. And hopefully you'll like it. This is, I did not draw this. This was sent to me by a good gentleman that I've been communicating with quite a bit. Bob up in Iowa, excuse me. Thank you, Bob. I sure appreciate the help here. I need all the help I can get. I love this stuff. This is a very neat program. It takes quite a while to get it, and I have a lot to learn, especially about the FFT displays, which are very important. The FFT display, as everyone knows, is a frequency domain type of display. An oscilloscope is a time domain display. You know, the horizontal axis is time, and in a spectrum analyzer, an FFT device, the horizontal axis, the x-axis, is frequency. So we get to see what's going on in the frequency domain. It's almost through, 90%. Okay, almost there. And I think it's just going to pop up and give us a display all by itself. I don't remember, but it's real easy. Nope, it's not, but that's okay. We're going to make a measurement again. We're going to use our cursor. We're going to go down here, and we'll put our current. We'll put our meter on the device, and we'll click, and there we get its current. Okay, now this one is run at a lot lower voltage, and it's actually run as a beam power tube and not a triode. It's not triode connected because the screen voltage is considerably less than the plate voltage. But if we go up here into the display and right click, and then we go to view, and then we go down here to FFT, it's on that resistor right there. That resistor is what we're going to look at, and we say okay, there's our display. Now that's pretty cool, right? We go, wow, I like that. Now what are we going to do with it? Now I think there's some unreal things about it. Our expectations might be a little high. Let me turn off this light. I see that there's a glare there now. Had to turn it on for you to see the calculator. Anything that's down here at like minus 200 dB, I'm a little suspect of. You can chop this stuff out. You can cut this off wherever you want. If you go over here to the left side and right click on it, you can change the scale to anything you want. Let's change it to say minus 210. 210 dB. See, we cleaned it up a little bit. That looks a little better, huh? Tektronix called that, they had a name for it. I can't think of it now. Anyway, baseline clipping. Let's look at this frequency right here. You have to look down here in the corner. This is 200 hertz. See that? Let's look over here at this one. What is this one? Well, that was 600 hertz. What is this one? Well, that one's a kilohertz. 1,000. So all we've got is odd harmonics. Well, what in the world happened here? Well, all of our even harmonics are gone. If we have 200 right here, we should have 400 if we have any even harmonics. We'd have 800 right there. They don't exist. See, you can see that's the area for 800. This would be the area for 400 if I can get it right on it, which it's hard to do. All we've got is odd harmonics. So we've got the perfect transformer and we've got a push-pull amplifier. And a push-pull amplifier by its nature suppresses even harmonics. And that's a good thing because most of the power is in the second harmonic. So it cleans it up really nice. First time I looked at this, I thought, well, that's really interesting. But anytime you get these FFT displays, you need to look at them really close because you may be surprised. I was very surprised with this one. And you can also, if you don't want to see all of this, like this thing scanned out to a megahertz way over here. You can, I think you can do this. You can take your cursor, say, put it right there, drag it, and create a window. And let's just go out a little bit past 10 kilohertz. Let's say it right there, and then let go. There we go. So we've got another display. Well, anyway, this is a very amateur version of using LTSpice and modeling transformers. There is a real challenge in it. I really enjoy it. I hope you guys get something from it. Hope you download the software and create your own. There are lots out there on the internet to be found and modified. You can cut and paste from one schematic to the other. I can't sit here and show all of that. I only know a little bit of it myself. But I know that there are you fellows out there and ladies that know much more about this than I do and can fly this computer in circles around anything I can do. So there you go. I hope this helps. And this is probably about as far as I'm going to take this. LTSpice FFT displays of vacuum tube audio transformers, unless I find something really exciting, and then I'll make another video on that. So thanks for watching, and thanks for all the help that I get from you ladies and gentlemen out there in YouTube land.